some papers under the general heading of composition. And Mahdi Saidi will start us off with a survey on service composition languages. Over to you.
Okay, let me share my screen. I hope you can see my screen.
Yes, we can.
Okay. Okay. Hello, everyone. I hope you're having a good day. So let me start my presentation. My talk will be on the paper that we wrote, which was about a survey on service composition languages. I'm Mehdi Saidi Nico, and I'm a PhD student at the Software Engineering and Technology Research Group at TUE, which is led by Mark van den Brand. So I will talk a little bit about the goal of this study that we did and a little background, and then the selected languages for service composition, and some evaluation and observations we had on that, and later about the ongoing and future works. So the aim of our study was to do a high-level feature comparison and assessment of some of the known service composition systems with a language-oriented approach. And we had 3 research questions. What are the available service composition languages? Which one are actively used? And their characteristics with respect to the SOA and language engineering. So some backgrounds. We know about web services and service-oriented architecture. That the modular pieces of functionality that are scattered over the web and through different mechanisms with service registry and service publication, and at the other side with consumers that discover these services and use them. We have this service-oriented architecture, and the way that these services are combined together and composed together. This is this is our focus in this work, and there are languages and systems for doing this composition, and we are focusing on them. So this is actually a very simple example for showing a workflow of a service composition, which is developed in EPAL language, which is one of the standard languages. And it is showing the flow of a process, which is about a loan, getting a loan. And it involves invocation of web services. So in service composition worlds, there are different approaches, techniques, and perspectives. So one of the first things is that they fall into 2 categories. It is either an orchestration or it is choreography. If we work with a central unit that is orchestrating and coordinating the flow of the process, communicating with the services and the order, then we have an orchestration. Otherwise, with no central units, we have a choreography in which the participants each play their own role. And finally, the process goal is fulfilled. The other way of looking at service composition is that they fall in a manual automated way of composition. Manual, of course, it happens at design time, which is limited. You cannot change it later, but in automated way, this can happen at runtime, and it is more dynamic. And well, it is more complicated. It's more complex. But there are techniques such as AI planning, semantic web that are useful in this area. Also, we have static and dynamic categorization, and we see that here the two extreme sides with early service binding and manual, we have static, and with late binding and automated way, we call it a dynamic service composition. So the scope of our work, it is on systems and languages that offer this service composition. And we looked at both academic and industry solutions. And from the 38 systems that we collected, 14 of them were selected. And mostly, I mean, there were some inclusion criteria, and the systems were considered if they had their own domain-specific language offering, or they were actively supported, maintained by industry or academic players. And there are actually other languages, other systems that have been developed over years, but they're not working anymore, or they're just pure academic works, only at a prototype level. They were not included. So here is the list of systems and languages that we included in our study. Some are standard languages such as BPAL, BPMN, and WSCDL, which are used for both choreography and orchestration. They each have, well, different purposes. Some are coming from pure academic works such as YAL, which is a famous one. Some others are pure well, industry solutions such as Amazon's step functions. And for our evaluation, we had 3 dimensions to look at these systems and languages, looking at general features such as the origin, support of ID, open source runtime environment, support for SOA concepts, composition model, target application, the domain of application, support for reconfiguration, and for SLE concepts, some other features such as concrete syntax, semantic, formal verification, execution mode. And this is the table that we finally built. And we have the set of features, the 3-dimensional features we have at one side, and the set of languages we selected, and each, with each of them showing which feature they support, which they are not, and how they do that. So a few observations that we noticed, that as I said also, many of these languages that we develop over years, they do not, seems they do not live long. And the other thing is that, well, there is this concept of microservices, and the promotion of this choreography that they should work together with microservices, but orchestration languages are still widely used, and some major industry players such as Netflix, Camunda, they are also they're taking the side of orchestration languages instead of choreography languages, but some other solutions are also taking a hybrid approach. That's another point. The lack of runtime adaptability, which is seen only a few of the languages, and which are academic ones, they support runtime adaptability. In industry, mostly they rely on manual composition instead of automated way of doing that. Also, we don't have strong service composition IDs. And again, the lack of formal foundation in the languages for service composition, especially at industry sites, which don't care about much about this topic. And well, the majority of the languages were supporting some cross-cutting concerns, such as error handling, some with scalability, some had deadlock-free design, and so on. So this was actually preliminary work that we conducted. It is not comprehensive. It was just a review to look at some of these known major service composition systems and languages. But there can be different ways to extend this work. For example, to apply the famous workflow patterns on these languages, or to extend the set of features and dimensions to evaluate these languages. For example, to look at declarative or imperative nature of the languages, grammarware, modelware, and so on. I'm also, for now, working on the business process modeling languages. And to start with, my focus is on BPMN, which is the dominant actually language in this domain. And looking at different ways on how to do analytics and management of these models, like clone detection, similarity, variability handling, and so on. So thank you so much for your attention. If you have any question or any feedback, I'm happy to hear that. And if you have any interest in doing collaboration in any of these topics, I would also be happy to, if you contact me. So thank you again.
Thank you. Let's see, I have a question. So was there, you said there wasn't much participation or much use in industry of these types of tools. Was there sort of a kind of predominant reason why you think there is that lack of adoption?
Adoption of what in the industry? I didn't get that part.
Well, if you go back 2 slides, you had in your chart that let's see, in your observations, one more, there we go. You said turns out industry side mostly rely on the manual composition approaches. So why do you feel that that's the case? Were you able to kind of pick up on that from y'all's survey?
Well, I think the obvious solution is that automated solutions, they are costly to implement, and they are more complex. I mean, yeah, so I think that's the reason. There are actually some works. I mean, there are so many academic works that they're using. For example, they are doing QoS, quality of service ranking of services, and rule-based mechanism to suggest right services at runtime. But these, what we notice, are mostly like in academic level, not in practice. they don't. I mean, they're not applicable much for now.
Okay, thank you. Stefan, do you want to ask your question?
I think it's just a follow on from what you just said. So if your analysis is that the problem of why it's not being used in industry is because it's too complicated, too involved, too costly in effect, have you got any thoughts on how one addresses that issue, or is it the case that service composition languages are effectively dead because they're more expensive than useful? Being devil's advocate here.
Well, I don't know really. I think more research needs to be done in that regard, maybe. But still, seems industry doesn't show much favor, or maybe, I don't know, there are some risks, I don't know, that they don't invest on it. Or maybe the current solutions are just maybe enough for now, are working anyway. So yeah, I think maybe more in-depth analysis should be done.
Thank you.
All right, thank you. All right, well, let's get moving to our next presentation. I believe Daniel, saw you on.
Yep. I'll just queue up here.
So I stop sharing?
Yes.
Just give me 1 second here. My computer's giving me a hard time with the antivirus and the webcam.
Yeah, those video viruses, they're really tricky.
Giving me some issues. Okay. Oh. There we go. Sorry about that. Just having an issue there for a second with the my software. Okay. And my presentation.
All right,
Okay.
so Daniel's going to talk. Great, you're all good to go. He's going to talk about a composition algorithm for reusable workflow models. So, Daniel, it's all yours.
Yes. Well, hello, everybody. My name is Daniel Devine. I'm a master's student at Trent University, and my advisor is Omar Allam. And I will be talking about a composition algorithm for reusable workflow models. This particular algorithm has already been used for use case maps in the context of reuse. So that is primarily the context with which I will start in, and as we proceed through the presentation, I will explain how that algorithm can be used in the context of other workflow modeling languages. So before we really get into things, I'm just going to make a quick note about use case map notation, so that people who aren't maybe familiar with it will get a quick idea of what it is. So basically, it consists of a start node, an end node, and a series of responsibilities. And there's more to use case maps than this. There's joins and splits in the path, and things like that. But we really don't need to know much more than this to get a sense of how the algorithm works. So, so here is the actual algorithm that's in the paper. It looks a little long. However, it's rather straightforward. It's kind of broken up into 2 parts, specifically a forward transversal part and a backwards transversal part. And I'll explain how that works for use case maps here. So here we have a very simple base use case map, and we have a very simple extension use case map, and we want to reuse the extension model with the base model. And in order to do that, we have a mapping between the base and the extension model. And we have a source node in the mapping. And generally that's kind of a partial node. It might be lacking a little bit of information. And what we want to do is we want to concretize the target node in the using the extension model. So the base model might have a little bit of incomplete information, and we want to use the reuse the extension model to create a complete model. So the first thing that happens is the algorithm grabs the mapping and determines what the source node and the target node is, and it marks the target node as visited. It then moves backwards along the extension model until it reaches a start node. After it reaches the start node, what it does is it looks at the predecessor of the source node of the mapping. And it's basically what the algorithm does here is it rewrites the predecessors of, or the predecessors of node 4 to be the successor of node 1, and it rewrites the successor of node 1 to be node 4. And then it deletes the start node of the extension model. The algorithm then, once it reaches the start node of the base model, traverses forward from the target node in the mapping until it reaches the end node of the extension model. And then in a very similar manner, it rewrites the successors of node 6 and the predecessors of node 3 so that they become connected. And then it deletes the end node of the extension model. And so after the entire composition is finished, you're left with a complete model. And you can kind of see how it just zips the 2 models together to get this nice composed model. And it simply deletes the source node in the mapping so that because it's incomplete, and you're left with node 5 there, which completely realizes node 2. So that's how that works with use case maps in the simple case. For a more quickly go over a more complicated case with multiple mappings. It does the same thing. It starts from the first mapping and goes backward, rewrites the predecessors of node 6 and the successors of node 1. Then it moves forward. Now, the only difference here is that when the algorithm reaches the base of the next mapping, or the target of the next mapping, sorry, in the extension model is that's where it stops. It doesn't have to go all the way to the end node. And the same with when it reaches the source node in the mapping, it also stops there, and then rewrites the successors and the predecessors of node 8 and node 3 respectively. The algorithm then grabs the next mapping and applies the exact same algorithm and works backwards, except when it sees that there's no predecessors for node 9, it jumps back up to the predecessor of node 4. And when it sees that node 3 has already been visited, it stops and it rewrites the successors of node 3 and the predecessor of node 9. It then moves in the forward direction, and you get the exact behavior that you'd expect, the same as in the first case. And it rewrites the successors and predecessors again, and you get this nice single composed model as a result. Now, there are some more complicated use case maps that can be created, and there's joins and splits and other things that can happen. However, I would advise taking a look at the paper if you wish to see how those more complicated cases are handled. Now we'll move on to a different type of workflow model and show how that this algorithm can be used to reuse other models in other workflow languages. So this here is a use case specification. In particular, it is restricted use case models. So this comes with a very specific syntax, and basically it consists of steps and flows instead of responsibilities and the various branches that you see in use case maps. And so this is an authentication model. This will be used as the base model for our model reuse example. And the source node in our mapping will be this step here. And basically there's a vertical bar there that just denotes that this needs to be kind of concretized. It's lacking some information. It needs some kind of authentication means in order to be fully realized. This case here is an auto log off model specification. And this is going to be our authentication means. So we want to reuse this model with our base model of authentication. And the very first step here is going to be the target node for our mapping. And this slide here, I just have this here to show that you can see that it's almost like there's a similar structure between use case specifications and use case maps for authentication. And the same kind of goes for our use case of auto log off. More than that, I actually wrote some code to show the algorithm working and kind of give you a visualization of what these kind of look like with their similar structure. So this is auto log off. Where's the other one? Okay, so this here is our base model of authentication. And one of the slight differences that you might notice between the actual use case specification and this here is that the first step, start here, has been added. And the reason you want to do something like this is, in the case of the extension model, is you end up deleting whatever your start node is, and you don't want to delete your first responsibility. So for some workflow languages, you might need to add on an extra node or something at the start to just represent that it's the beginning if the first step represents some kind of functionality or requirement that you don't want to remove from the actual model. And in this case, I also used the post condition of the use case specification to represent the end node. So that is kind of how you can visualize the authentication model, base model. And then here is the model that represents auto log off. It's a little bit messy. This is all done using GraphViz, so it's automatically laid out. But again, you can kind of see here that there's kind of a node here that represents start, and the post conditions that represent the end node. And when that all gets woven together using the algorithm, you end up with this. This is a representation of the final use case specification. And we can see here that the start's way down here, and it's a slightly more complicated result, which is what we'd expect when we're weaving together two models. And this is what the final use case specification would look like. So we performed a tiny case study just to show how this might provide some benefits doing reuse with an algorithm like this in a workflow language. And here we have a set of models that represent authentication. And in the same way that so far I've shown how authentication can reuse auto log off, as we can see here, there are other ways that you might want to configure authentication with different models that you reuse to use other different kinds of authentication means, or to make your authentication more secure. And in this case, we had 7 different models used for extension, and on average between models there was 1.14 mappings. And using just these mappings, you can produce 44 different variants of authentication, which is quite a few different variants. We also did a similar calculation for a set of models for online payment, and online payment might even reuse authentication for let's say you're making a website and you're creating online payment and you want to do authentication with your online payment. You might want to reuse authentication here. But in this case, to configure authentication, there was 11 different extension models, and there was an average of 1.55 mappings between all the various models to produce approximately 378 variants. And so this shows that the algorithm can scale very well when you're adding or reusing a lot of different models to configure a base model. It scales very well, and you don't need too many mappings. You don't need some of the complexity that you might need with some other forms of composition, where you need to pattern match or add advice or various things like that. So just to recap, basically we went through how the algorithm works, and how there's 2 parts to it. There's a traverse predecessors component, and there's a traverse successors component to the algorithm. We looked at how use case specifications kind of have a similar structure to use case maps, and we looked at kind of how that can be visualized. And then we looked at kind of the benefits and some of the value that you can get out of using an algorithm like this. So that is my presentation. Thank you very much for your time. Do you have any questions?
So I think we have time for just a quick question or two. Somebody have any in the chat? I was going to ask a question. This may be a kind of a dumb question, but what happens when you have like some kind of conflicts or you know, when the things don't merge well, or they don't merge in a sensible way? What do you all do to kind of either alert to that or, you know, work around that?
Yeah, so there's some basic properties to this algorithm. One is you could probably infer from the example, which is that it tries to maintain the order of the events prior to the source and the target node in the mapping. And I guess what you'd be talking about is which of those events comes first. Or some other more complicated things. Basically, in the original research and in the paper, it talks about how the algorithm is used, and if you use the algorithm in a very particular way, you don't end up with some of the funniness that you think you might get. It's something that I've been kind of writing a little bit of a paper about. I've kind of started on it a little bit. I'm not sure entirely where it will end up, but for the most part, it does maintain that order And it is kind of hard to visualize what the result will be when it's kind of zipping back and forth in the more complex cases. But to directly answer your question, it's not like there's a validation algorithm yet that that could report any of the weird cases. Yeah, so if you're looking for something very specific, you need to kind of really understand how the algorithm works and use it appropriately to get the results that you're looking for.
Cool, thank you. Stefan has a question. I'm gonna skip your question, Stefan, so we can get to the keynote and make sure that Robert has plenty of time because we're running a little bit late. So thank you very much for the presentation.
Thank you.
With that, I will hand it over to Andreas to introduce our keynote speaker.
Yes, thank you very much, Taylor. So yeah, I have the pleasure to introduce Robert Caban to you. Robert is, and that's now a very long and impressive title, CEA, Software and Systems Environment Chief Engineer in the Systems Engineering and Formulation Division at, and now comes the kicker, NASA JPL. So Robert is building the big systems, which will be very interesting to talk about. Actually, he works on providing an environment for modeling and supporting systems engineering. He's one of the drivers of the open MBEE community. And he acts as the NASA representative at the OMG for SysML to align the different modeling aspects. Before that, he worked on applying MBSE to large telescopes and to particle accelerators. So the really interesting systems and the systems that need modeling very direly. And in his keynote, he will discuss the state of practice at JPL on system level executable modeling. And he will do that from a practitioner's perspective. So, Robert, thank you for sharing your decades of experience with us. And I'm looking forward to your presentation on multi-engine simulation around SysML and future use for executable modeling in that context.
Okay, so let me share.
Daniel, you will need to unshare your screen before Robert can share his screen.
Right.
Now you should be able to share, Robert.
Okay. See my screen? Not yet, because I have to push a button. Okay, here we go. Okay, well, first of all, thank you for putting me last. So I had some minutes to wake up because it's still quite early here. And I'll try to fully wake up by the end of the presentation. Also because my boss is online, so I better be, otherwise I might get fired. So thank you very much for the introduction. That allows me to skip 2 slides. As mentioned, I work for JPL and have been heavily involved in model-based system engineering for more than a decade. I worked a long time on telescope and instruments. And here is the list, and I worked a lot of time with Luigi, who is also online back at the European Southern Observatory. At JPL, I've been involved in a number of space missions, helping the projects to move gradually to a model-based system engineering environment. And as you mentioned before, I lead the team that is responsible for providing basically the digital infrastructure for model-based system engineering and data analysis. So where are we? So we are located in Pasadena, California. It's still dark outside. We are a so-called federally funded research and development center. So we're NASA-owned, but funded and operated by Caltech. So we're the biggest division of Caltech with around 6,000 employees. You see the picture there. The first few years, I didn't see the snow on the mountains. Last year, I think I did, and the year before. And now it's more like smog because of the fires. It's getting better. Here is an overview of our past missions with all the robotic space missions from landers, orbiters, surveyors, and rovers in particular. And the most prominent one, which is on its way to Mars is Mars 2020 Perseverance rover. And let's cross our fingers that it will land safely there. So I've been building control systems most of my professional life. So I come from the side that I've been using modeling from the very beginning to produce something, right? I have to deliver a production system that operates some machine typically. So I will drive that presentation from this perspective. So why do we want to have an executable model at all? And in particular, why do we want to have it at system level? Because most of the system engineers, in particular, not in particular JPL, I think at JPL also, the main tools are PowerPoint, Excel, and Word, right? And maybe some requirements management system. And what I often observed is that the behavior and what the system is supposed to do in terms of operations comes very late or is described in some narrative. So to have an executable system helps us to describe that system much better and to gain some understanding before we actually start building it. We want to validate it in the requirements and the behavior in the system model, and we want to understand that those requirements better. Usually they come in some text blob, and they are, of course, super ambiguous, but helping with the system level model, we can formulate it in a more precise way. And then we want, of course, to analyze the as-designed system, how it reacts to user interaction, to test data, scenarios, and certain analysis related to budgets, like error budget, resource budgets, and timing constraints. So we want to also to explore not only the sunny day behavioral system, but also the rainy days. So what is not desired by injecting faults and see if the design can cope with that. And before we start actually implementing it, to check the consistency in logic of the design as good as we can, because there's always time constraints, of course, and you can only do so much. We want to understand the roles of the different components in the system at the logical and the physical level. And we strive for having a kind of consistency across all these artifacts that we produce, the model, the code eventually for a control system, the documentation, simulation, and analysis. So that brings us to the topic of model-based system engineering. And what is model-based system engineering? It tries to formalize all the things we do, from requirements management, design capture, analysis, verification, validation, and document everything properly. And as I said, the many tools are Excel is a prominent one, and PowerPoint, and that is not super formal. So you get a lot of inconsistencies, duplicates, and so on. Usually you use some system modeling modeling language to do that, for example, SysML and or Modelica, and some method like OSAM, the object-oriented system engineering method. So those three things are coming together and try to carry out your activities and tasks with supporting modeling techniques. So this terrible picture is from the early 2000s. It's where I kind of started to get involved in model-based system engineering, where the big promise was, okay, today we have all these documents as in the artifacts I mentioned before, but in the future we will have only models. I mean, moving from a document-centric to a model-centric world, to have our requirements for interfaces, the system design, and so on. And I pitched that a lot of times, but of course it doesn't work. The documents won't never disappear. People want to look at the documents, but we want to support them and relate them and actually create those documents from the models. And that's a whole other different topic that's OpenMB related that I will talk about also a little bit. but the models have started to play a much bigger role in this exercise. So before we go into what the current state is, let me put on my archaeologist hat a little bit and share my experiences from back in the days, where I think many of you are much younger than I am, so might not even were born at that time. So the first time I got into touch with something like system level modeling when I worked at Alcatel in the 90s. They had some system that was based on the specification design language, from which actually the UML sequence diagrams originated. And it was a kind of a nice system with graphical and textual representation. You had some semantic checker, a report generator, a code generator, which didn't work. And but you could specify your system as an interconnected set of abstract machines. And it was used for telecom systems to specify them. But it was super cumbersome to use. It was one basic state machines and sequence diagrams, and that was about it. The second time I got into touch with something was when I worked at CERN, and they used the system which was called Foresight, and it was really very comprehensive. You could capture your system requirements and design, and you had a graphical executable GUI where you could see all your state machines executing. You could combine it with some action language, which was derived from Ada, and it was a discrete event simulator that was used to model basically the experiments of the LHC with 10,000s of channels. And it was nice. I mean, back in the day, almost everything you needed. But then it died, and it died because it was a proprietary system. It did not integrate, it was not open, so it just disappeared. And then it took a while. Right? So here's some history. So 94 was the Neutrino thing, UML 97, and that's basically, I mean, before that, I used all the stuff with CodeJordan, Grady Booch, all these methods. And then I jumped on UML. SysML came 2007, so 10 years later. And still, both of them initially, it was mostly boxes and lines. And there was, as far as I understand, also no intention to have to have it executable. Right? It was a description, an English description of of the semantics, but that was not really sufficient to build something. But people still build something with it. Somehow, the big change on the professional level was when SCXML came out, the state chart XML standard by the W3C, which the draft was in 2010. And that's when Luigi and I started to use a more model-driven, or actually a very model-driven approach to develop our systems, right? To have the model and to produce something that actually runs on the target system. It got standardized in 2015, so it took also several years. FUML improved the situation with UML quite a bit, but still. And then it took still a number of years to get the precise semantics for compositional structures and the precise semantics for state machines. And thank you, Ed, for that. He's on the call, I think, as well. But quite a bit. And in between, people did something else, right? They had to fill in the gaps of the specs because they wanted to provide a tool that where you can execute and simulate. So 2011, another tool came out that made the first attempt of being like a framework, not just a specific tool. And it took, again, like a number of years to get it to maturity. But I want to highlight three things which are important here. First, that it's multi-engine and pluggable. So it's a framework that provides you the ability to plug in different simulation engines and different languages. and it's standards based, right? So it implements the SXML, PSSM, FUML, and SysML standards, and that is kind of very important. That's the big difference to the other tools that I mentioned before, to be standard based and open, because then you can rely on something. But of course, the specs are imperfect, so the gaps have been filled by the tool vendors, and that is a problem from the practitioner side, because one tool does it a little bit different than the other one. Right? So I'll get to that in a second. And yeah, so with that framework, that was 2011 was the first attempt to kind of do some kind of MUS system model based on SysML. And it demonstrated then that you can integrate state machines, parametric models, activity and interaction models, and they can work collaboratively to describe your system, to specify your system, and to analyze your system. And that was kind of very encouraging, because you had a standard-based open environment that you could work with. Of course, it took some time to mature. So what's the current state of practice? So at JPL, so here's some selected JPL applications. The 30-meter telescope, SMAP, which is a satellite, Psyche, which is flies to an asteroid, Europa Lander mission concept, Mars sample return. And what we do there mainly is to capture operation scenarios. So what's going to happen if the lander lands on Europa, and what will it do if it will land on ice in deep snow? How can it examine the site and take samples and so on? And to model that and capture that, we use activities, state machines, parametrics, and sequence diagrams to produce a number of artifacts like interface control documents, functional design documents, analysis reports, and also code eventually, hopefully. So there is this slow and still slow transition from writing up everything in a document before and having a model to capture it. Still, the engineers sketch many things in Visio first or in PowerPoint, and then we help them. So my team helps them to use our environment to formalize that workflow. Right? They sketch something up, we help them to formalize it in some SysML model, and we make it executable. We help them to make it executable so they get interesting insights into their specifications. So I picked two examples, and I picked those two because one is actually the whole model is open source, which is the 30-meter telescope, and there we started, maybe 5 years ago, about 5 years ago, for one subsystem, a fully model-driven approach overall, and then expanded it into other subsystems. But it works in the kind of hybrid approach. When you use traditional system engineering for your deliverables, and because people are used to it, and you can trace things more simple. And we use the model-based approach to mostly or almost exclusively to understand the behavior of the system, right? For which is was the stepchild for many years. The behavior was always kind of a stepchild, and to have this rich capability of modeling and executability to represent this kind of complex systems and combine the two. So what are the MBC objectives of that project? So we capture the operational behavior, identify the involved subsystems, right? Because sometimes you don't know, you start somewhere with some functional component, and how does it interface with other components, what are the other components it has to interface to, what are the interactions between those, to define requirements, so like timing requirements for algorithms, and also interfaces to other subsystems, create a fully executable SysML model, and we have successfully achieved that with all the problems that appear. But we have a fully executable SysML model that is using state machines and activities and also sequence diagrams. And that enables us to analyze the system design, right, and verify the requirements for different aspects. How much power does it consume? What's the timing or duration of all these operational behaviors? Do they satisfy the requirements, at least of the S-design system, for error, to calculate error budgets and so on, but also to produce engineering documents. And the goal was to use only standard languages and techniques and commercial off-the-shelf tools where we can, and to avoid any kind of software development, because it's a very small team with a lot of work, so there is not much room for experimentation. So here is one thing that comes out of that. It's a timeline produced by the simulation where you see basically all the components involved in one scenario, in the states they are in, and how long they're in a certain state for that scenario. So why does that help? It helps because we can quantitatively see what the components do, right? And we always needed that information, but it was extremely costly to produce it, right? With PowerPoint and Excel, you can imagine what it takes to produce something like this. I mean, to build a model is also expensive, but that's somehow in the beginning. If it's expensive probably to build that model, but once you have it, it's cheap to update. So when we built the initial framework and identified the patterns, to add new things became a routine. Right? Identify a new use case, capture the use case, model the behavior, and analyze it. So there is a learning curve in the beginning, but it flattens out. The other example is from SMAP, and there it was used to specify the behavior with the target to get a logic design for the fault protection. So if a fault appears, how do you recover from that? How do you identify it? And it was a set of so that's a few years back, 8 state machines with a couple of hundred of states, and we used the SIMUD executable model to identify the behavior of each component, how they interact, the interfaces, and so on, and to check the initial logic of that design. We also applied, to some extent, model checking to that, and as you can imagine, the state space explodes very quickly. But they could get some reasonable results like five years ago. But I see also now that we can do better nowadays. So we're also working on a framework or a service for model checking to enable that. But the executable model is the key. That's the first thing you have to have, right? So to produce something which is not just boxes and lines. So in that case, in the SMAP case, it also generated like sequence diagrams automatically from the execution. So the system engineers would print them, put them on the table, and look, because they like to print things, and look at which components are interacting, how they're interacting, which kind of messages are flowing between them. So the model represents the system as an authoritative source, right? So we used to do this analysis, but they were expensive. As soon as we have the executable model with specified semantics, we can do them, and we can do it with confidence. So that's a kind of a big step. But of course, there are a number of challenges, in particular with adoption. So my background is computer science, so I can somehow digest all these things that happen in the background, but many people are not, right? So I think that the problem with there's a lot of semantic issues, variations across the standards and the tools, and I list here just a few. So if you use one, like some slight subtle difference between SCXML and PSSM, and then across the tool, and then in the beginning you somehow never know, is it, if the simulation doesn't do what you expect, is it a bug of the tool, or is it my model wrong, or is actually is my model in my head wrong, right? So, and I want to focus only on the model that is wrong in my head. I don't want to understand if the semantic is correct, is compliant with the specification, or if the tool has a problem. I don't want to deal with that, but I have to. I mean, I still have to. So you shouldn't have a computer science degree to do that, in particular if you have Excel and PowerPoint as your main tools. And we see that in other languages as well, right? I mean, Java developers, they don't necessarily know anything about the abstract syntax or grammars, and yet they produce a lot of Java code, and it works, right? And the same thing we want to have for our system engineers, right? We want to have the system level execution analysis to be compatible with the system engineering practices, and that's quite a challenge. So another aspect is code generation, right? You have the executable model. You want to you can simulate it, but now you have actually captured a lot of the semantics. So how do you, in particular for behavior and control systems, how do you bring it to the target? And over I don't know 30 years, as I said, basically starting in the 90s, I've tried to use let's say code generation, right? Transformation rules and so on, and feeding it, trying to feed it back to the model if it changed code, and there's always something which doesn't work. In particular, the round trip, I think, never worked. And if you actually generate concrete code, right, with some arbitrary rules, and produce some arbitrary code, you have also run in kind of a lot of issues. The code might be hard to understand, hard to debug, hard to change, and you lose somehow. You still have the transformation, but it's kind of a disconnect. So instead, what we would like to have is to have more like the model of a 3D printer, right? You have your CAD model and you 3D print it, and there it is. And if it doesn't quite fit, then you can still, use your Stanley cutter and shape it and update the model to make the model better and produce another 3D print, right? But it's more like a different, and for the executable model, it's similar, right? You want to have the same model that executes running on the target system. We don't want to have anything between, right? It's just want to view it as a different level of execution and maybe serializing in a different way. And that's kind of different from generating code. And the first step in that direction was the use of SCXML, because you have your simulation model. You can have you use the operation semantics of SCXML to simulate it, but then you produce this XML file, and you use an execution engine which you can test as much as you want, and should just load that same model that you created and simulated and run it on the production system. So that's more the direction we want to go, and not produce thousands of lines of code. And that enables us to do a lot of things. I mean, we can change that file easily, and like we can change the 3D printed part and improve the model later on. Right? So that's more the way we want to go. So what are the enabling technologies? Right? Where are we heading to? So the first thing is to think about the let's say the traditional V model, right? You have on the left leg, you have all the requirements flow down, then you implement something on the right leg of the V. You have all the verification and validation activities. And nowadays, often you try to, there's documents flowing down and test plans flowing up. But what it really has to be, we have to connect those things along the legs, but also between the legs with a set of models, right? And those models have to be connected as well, right? So we want to drive it down from the science model to really to the subsystem models and to the implementation, right? So we want to have requirements management model based, the architect design, the analysis, the V&V, right? And ideally also the implementation. So the model becomes the connective tissue in all these exercises, right? So nowadays you might have some model actually. So people build models, but then they copy paste everything into a document and give it to the person, for example, for flight software to implement. Right? So you have immediately a disconnect, and then we produce test cases based on that code maybe. Instead, we want to have the model that connects all those things, right? So we can keep the documentation code, the test cases, and the analysis connected, and they're not anymore a disjointed picture. So that's this transformation that we are transformation in terms of the culture, right, and the technology we want to work on. That comes, so another objective is to build some end-to-end goal-based executability framework. So you have like produce a system model of the control architecture that also enables autonomy. You have an executable set of requirements, you clarify the understanding of the control architecture, perform the analysis and build transformation. And the analogy I draw here is with Google Maps. Right, so almost everybody, at least in the US, uses Google Maps. You enter your destination. Google figures something out and directs you by goal. Okay, turn right, turn left, go straight, and you follow these instructions. You're becoming Google gives you a goal, and you try to perform this goal to your best abilities. If you can, you try to turn right at the next traffic stop. And you do whatever is necessary to do that. So you're trying to achieve that goal. And if you can't, then Google will figure out something else, right? You missed the right turn, and Google rerouting. Well, it recalculates the network of goals and gives you new directions. And that's also very important for a control system, right? Instead of procedurally prescribing every step that you have to do, which is hard to change, you want to move to a more goal-oriented framework. But it should go the whole way, from the design, analysis, simulation, to the implementation. The second part is an environment, a model-based engineering environment. And a key role plays there the OpenMB community. And today there's actually, in 45 minutes, there's the first OpenMB workshop at the models. We had a few at the in COSI, at the International Council on System Engineering, with a lot of participants from the practitioner side, from industry mostly. But this community built over the last, let's say, 5-6 years, and they all have the same goal. They all need a model-based engineering environment, right? to handle the increasing complexity of the systems and do this transformation of the system engineering culture. And it's a community for software and for models. So it provides a number of apps and services that build the core also of our digital infrastructure to manage models, to close the gap between engineering artifacts and the documentation you have to provide. But it also contains or people contribute models that can be reused, right? And it's a very good forum to exchange ideas and the challenges that we all face. So the community has been growing quite a bit. We are now over 400 members with participants and adopters all, from various industries, as you can see, aerospace and automotive, but also academia. So that has become a key element in this strategy. And the goal, the vision of OpenMB is to produce this global engineering ecosystem. Right? We want to have this connected ecosystem because we are not only in an isolated place, but we, for example, JPL has to interact with other NASA centers, also with ESA across the ocean. And they all produce some engineering artifact and documents, and often disconnected. And there are two elements that are part of this strategy. One is Jupyter as a central piece for multi-language capabilities to connect modeling and engineering, and SysML v2. And Ed, I think Ed gives a keynote today in the workshop. I think there was a tutorial on Friday. So SysML v2 has evolved, I think, over the last years, really in a very good direction. I think we have already now a stable specification, or a good specification, that makes me very, very hopeful for the future. But this engineering ecosystem, you can compare this engineering ecosystem to the web. Right? When I worked at CERN in 1990, and the first web server went online, and with OpenMB, the first engineering server went online. So that's so I invite you to join the community, to attend maybe the workshop today, or the OpenMB event tomorrow at the Industry Days, where a number of the community members will present their work. Jupyter is a key piece in this strategy as an analysis and visualization hub for models. It provides this very rich, interactive, exploratory, and web-based environment to connect modeling, engineering, data science, and a number of other things. SysML v2 is also a key element in this strategy. It's not anymore constrained by UML. It has a new meta model. It's based on formal semantics and has a robust visualization with a flexible view and viewpoint specification. And also, most importantly, it provides a standardized API to access the models that you produce. And we also have, meanwhile, let's say in the reference implementation, an integration with Jupyter. So you can put together in Jupyter, create your model, visualize the model, and combine it with documentation. And hopefully in the near future to actually analyze it also. Another key element in all this executability and simulation world is FMI. I'm not sure when it was initiated, but I think it may be 10 years ago, and I think it was Daimler. Meanwhile, there's a whole lot of organizations supporting it, and 100+ tools, and it enables sharing and integration of different executed models to enable co-simulation. So that is also in this world there will be not the single model that will do everything, but it will be a federation of models to enable you to do the analysis that you do, and FMI plays a key role in that. And for SysML, for the current SysML, I think we haven't been able to produce FMIs. I hope with SysML v2 it becomes much easier to produce a functional mockup unit that you can run in a co-simulation with other models like Modelica, for example. Modelica is based on FMI standard for executability, so it would be nice to combine those two. Another aspect is the model management, and so it has been and still is a big challenge to how do you organize your models that you don't get crazy, right? With all this, if it becomes too big, it becomes unmanageable because you cannot configuration version control it properly. If you divide it up too early, it's hard to manage those dependencies as well between the packages. So Conda shows how that should work. It could work from the Python world, and we want to have something similar for the models. I want to have some framework, and Conda probably could manage that to manage the dependencies and of my self-contained models. Right? I want to take something. So here it is. Reuse it, integrate it into your model, without trying to disentangle it from all kind of other things. So to enable this distribution of self-contained packages and model reuse, right? So to broadcast these models, like on Conda channels, you broadcast Python packages. So this SysMLv2, Jupyter, Conda, and the FMI are kind of key pieces in that picture of the future model-based engineering environment. Also, everything in related to executability. So here you see, and that's my final slide, the next generation system engineering dream car. Jupyter in the center, system is the chassis, SysMLv2 is the engine, FMI and Conda are the wheels, and OpenMV is the driver. So thank you very much for your attention. Any questions, comments?
Thank you very much, Robert. I would love to get a copy of that dream car, so to say, and drive around in it.
I'll send it to you.
But yeah, as you said, do we have questions from the audience? I see a couple of comments. There's a question by Göril Hedin. Göril, do you want to ask Robert yourself?
Sure, yeah. So thanks for a very nice talk. I was wondering, when you talked about modeling, I wasn't sure if you talked about modeling of the control systems or modeling of the physical systems that the controllers control. So I'm just wondering, do you see some fundamental differences between these kinds of modeling? And would you use the same modeling approaches for both, or how would you combine them? Would you use FMI?
So that's something we're trying to integrate. So I mean, we use SysML for, let's say, high-level modeling of the say functional behavior, right, and specifying the behavior of the system and its architecture. But we're trying to integrate Modelica into that for the multiphysics aspect. Right? How that? I mean, there are some integrations which are already there, but that's something we are exploring, how we can combine those worlds and make them kind of a seamless experience. Right? So yeah, I think SysML has its purpose, and I would not model details of a multiphysics system, but it can provide the basic, or model the architecture, the interfaces, and then we have to get that into for example, Modelica, and add all those details to perform the multiphysics simulation and analysis.
Okay,
so yes, so it's the multiphysics and the behavior. So it will be multiphysics to build your sensors and actuators and how they interact physically, and state machines to drive all that from the control system perspective. Yeah.
Thank you very much. There's another question from Benoit. Benoit?
Yeah, thank you so much. This is Benoit Combemal from the University of Rennes in France. Thank you so much for your great talk. That was a very nice one, and I heard a lot of new stuff in it. And especially, I discovered OpenMBE today, and I was just wondering if it seems to be already driven by industry, and I was just wondering if there was some specific expectation in terms of collaboration with academia, if there is any way of collaborating.
That's an excellent question.
Yeah, please go ahead.
So yeah, as you say, the OpenMB has been driven mostly as a community from industry, and I've been participating in the models conference on and off, and last year I was there in Munich, and there's this rich community of academia in the models community, right? And our dream is somehow to bring the academia, the industry, and the vendors somehow together to help to produce the dream car, right? I mean, I see all this. I saw the presentations, and there's a lot of ideas, and I think I would like to get together, like from the practitioner, from the industry, the requirements, academia to evolve and build the ideas, and then the vendors to commercialize that and make it available. That's somehow some combination of that. And that's actually the main reason why, or one main reason why we have made some effort to organize this workshop of OpenMB today, and to organize this OpenMB event tomorrow at the Industry Days, to bring those three communities together, right? From the industry, academia, and the vendor part. So yes, please participate.
Okay,
And
thank you so much.
Thank you. Erwan, you also had a question.
Yes, thank you for the very nice presentation as well. Really enjoyed it. Sorry, I arrived maybe, I missed the very beginning of the presentation, so I hope my question is not about that. I was simply curious, the presentation was very centered around SysML, and I was wondering if in the decisions or the discussions that led to such processes, did the idea of having not only one big modeling languages that encompasses everything, but instead of having that, having lots of modeling languages, namely domain-specific languages to model different facets of the model systems, was considered, or was quickly driven away, maybe because of constraints such as having one big all-encompassing tool that can manage everything at the same time?
Yeah, no, definitely not the latter. So the model-based engineering environment that we want to have is supposed to be a multi-paradigm environment, right? SysML has been historically a key part because that's somehow because it's a standard, right? And we start with that, and we got some good results. With SysML v2, that because of its architecture, and Ed can talk more about that, and it's because of its architecture, it should enable also DSLs on top of that. Modelica plays another big role for the multi-physics part. So we're trying to get the best of breed environment, whatever language there is, as long as it's open, standard, and there is enough support for it, right? I mean, cannot be some niche product where there's one person in the world that understands what to do with it. So we want to have some kind of commodity, right? We want to roll it out, give it to the users. There must be training available, and so on and so on. So yeah, it's a multi-paradigm environment by choice and by design. And for for system level and architecture, it's currently dominated with SysML, FUML, so it's a multiplicity of standards. Modelica is coming into this picture. JPL also has a big history in building its own environments and languages with all the disadvantages. But yeah, we want to have a multi-language one, and if it fits into the overall picture and helps us to achieve our goal, there is no really a limitation.
Thank you.
Yeah, thank you very much. And we have time for one or two quick questions. The next one would be from Federico. Federico, did Ed answer your question already?
Yes, I saw that. Thanks.
Sorry, you were very silent.
Can you hear me?
Okay, you muted yourself again.
Yes, sound
and-
problems.
Federico, another try? Otherwise, we move on to the question of Chris.
Now maybe we can
You
circle
guys
back
hear
to
me?
him. Yeah. Now, yes, I heard something.
Okay, yes. So thank you for the great presentation. But as Andreas was pointing out, Ed already answered my question, so you probably can go to the next one.
Thank you, Federico. So Chris, you also had a question.
Yeah, I was just curious, how much of this environment exists at JPL today, and how many languages does it support?
So that's my boss, by the way, speaking here, who is also on the OpenMB leadership. So, I mean, we have started to support FMI and FMU. We have Conda on the software side. From the executability part that I showed, everything that you saw is there and working. The languages that are supported. So there is also another part of the languages that I forgot to mention is like MATLAB and Mathematica. That is used at JPL. So we are in the environment. We are trying to integrate, and that's also the role of OpenMB, right? We want to have some repository or a number of repositories that enables different engineers from different disciplines to interact with each other through a model-based service. So there could be one using SysML to build an architecture. A second one extracting some information and do something in MATLAB, process it and produce something else that is part of the system model, or with Mathematica, or with Python and with Jupyter, because a lot of people actually use Python, right? And actually, if you look at that, you can consider it also as a modeling language in some way, right? But it provides this accessibility to this environment and to the data that we provide. And the Modelica also comes into the picture. So there is a number of languages and supported in this infrastructure that enable the engineers to access and exchange and propagate data through that environment. Does that answer your question, Chris?
Yes, thank you.
Okay, thank you, everybody. Are there other questions? Otherwise, we're at the end of this iteration of MLE. Thank all of you. Thank you, Robert, for a very inspiring keynote talk. And then all of you enjoy the rest of Model. Thank you very much.
Thank you. Bye.
Thank you so much to the organizers.
Thank you.
Thank you and good job.
Thank you.
Thank you.
And workshop.